Okay, so let's start. So this class is different from the other two classes. I will talk really about black hole perturbation theory. And I have two topics to cover. The first one is the Mathisson-Papapetrou-Dixon theory, which is a beautiful theory for describing objects with spin. So we are very familiar with geodesics and with particles without spin, but it's interesting to model also with spin, and there are different effects. So in this class, I'm not going to concentrate about the gravitational back reaction. It's called the self-force theory, and it's very long to present. I will concentrate on how to model finite objects without the gravitational back reaction. And later on today, we will we'll cover the quasi-normal mode ringing. So let's look at this problem. We consider the small mass ratio limit of the two-body problem. So when you have a small mass and a very large mass. So if the body one is a point particle without any internal structure nor gravitational back reaction, its motion is determined by geodesic motion in the metric generated by the second body. So at the beginning, it was a postulate when Einstein formulated his theory, but then he proved that it follows from Einstein's equations. You just take the two-body problem in full general relativity, and you take a suitable limit, point particle limit, and you find that it has to obey a geodesic. So a modern proof is found in these references. So it's very useful, this approximation scheme, because of the uniqueness property of black holes. So the stationary black hole is a Kerr black hole determined only by two parameters, the mass and the angular momentum. If the big body is actually not that big, if it's less than 3 solar masses, it can be a neutron star. And in that case, it's determined by two infinite sets of stationary multiple moments. So it's still useful, but less universal. So we look at this problem. So now let's imagine the first body, instead of being just without any structure, is an extended object, like a neutron star or even a black hole. Not a point particle. So we need a more general theory of motion. So there is an integral structure, and there's also this back reaction that would change the overall metric. And so those are called gravitational self-force correction, and I will just ignore them. I will now just concentrate on the intrinsic motion inside of the fixed Kerr or fixed metric generated by the second body. I'm not going to limit to Kerr only, it can be a different metric. I will just need to say that there is a background metric where this extended object moves. So the space-time diagram of this small object, it will have some Ward line, Ward line inside the object. So typically it's the center of mass, which is a good Ward line as a reference Ward line. And the object has some finite extent, and it just moves in space-time. As a reminder, it's good to know for geodesics how to describe the motion. So you need an action principle. This is the action principle for the time-like geodesics. So it's determined only by a single quantity, the mass, and the interval of the proper time. And as you know, the proper time is given by the square root of the line element here, contracted, where x star is the trajectory of the particle with respect to proper time. So you can parameterize with respect to any time along the Ward line that I call lambda, so that it becomes metric independent. So lambda is metric independent, but tau is metric dependent. So you can substitute it in there to get the explicit metric. And then the stress energy tensor is a variational derivative with respect to the metric times 2 over 1 over square root of minus g. So if you compute this, well, you get the mass here, you get the square root of the denominator, which is d tau over d lambda, a factor 1/2, a minus sign coming from here, and then these terms here. And so overall, they combine to give you this. And that's the stress energy tensor of the point particle. So as a first exercise to wake up a bit this morning, please try to show that the conservation of the stress energy tensor is equivalent to the geodesic equation. And the easiest way to compute this divergence is to use this formula for the divergence. So if you have a divergence of a vector, you're familiar that you can replace this divergence by a derivative by putting a square root of the metric here and here. And here, since you have an extra index, the current derivative will also act on that index, so you have an extra Christoffel symbol. So you have these two terms. So in here, the dependence in x is only in the metric and in the x here. This u only depends on the proper time. It does not depend on x. Okay, so I'll let you try it on a piece of paper. Can someone tell me if you did it already? No answer means that you are still computing. Okay, do you think I should move on?
I think it's okay to move on.
Yes, okay.
I think we need to.
Reacting. Okay, so we use this equation. This is the definition of the stress energy tensor. So I just act using this formula. So the first term, the square root disappears because of the square root here. I have just the derivative that acts on the only thing that depends on x, which is the delta. And this square root here, I put it in front. And then the other terms is the gamma contracted with the two indices here, which are the velocity, the tangent vector on the geodesic, and times this term. So now you have use this property that if you have a derivative with depending on x that acts on the delta, is minus the derivative acting on the x star. So if you contract with a u, and now u contracted with this partial derivative, since u is the derivative of x star mu with respect to tau, using the chain rule, it's just a tau derivative. So this term can be replaced with a minus d tau, d over d tau, and you can integrate by parts because you are on the word line and you ignore what's happening at the very end of the word line. So you arrive to this, this term here. So together, these two give you exactly the geodesic equation, this equation, or in covariant form, this one. Okay, hope it's clear. So for extended objects, instead of having just the mass now, the stress tensor of the object will contain additional terms, the spin and quadrupole and higher multiples. So the main point is that the equation of motion follows from the conservation of the stress energy tensor. And we will want to define conserved quantity from this stress energy tensor using some vector fields here to be able to define what are these spin, how to define the mass and the quadrupole and so on. So we want to define quantities like this one. So now the question is, how do you define the stress energy tensor of the body, and how do you define this vector to be able to define your mass or spin in more generality? So let's review a bit vector symmetries. So when you have a killing symmetry, it's a symmetry of space-time. That means that the lead dragging along that vector does not change the metric. And the definition of the lead derivative is it acts on the tensorial indices. So in this way, so we replace the tensorial indices using a derivative of the metric, the derivative of the vector. And there is also a term which is the vector acting on G, because when you lead drag, you actually move the space-time point. So by moving the space-time point, you have that term simply by a Taylor expansion. And since this is a tensor, you have this mixed, this tensorial type relations as well. So in total, this is the Killing equation. And you see that this is a combination of Christoffel symbols because it's the derivative of the metric. So you can use that to rewrite these derivatives by a covariant derivative, and then you can reabsorb the G inside. So by covariance, you can rewrite it this way. So in Minkowski, in Cartesian coordinates, given by CT and X, these equations simply are given by normal derivatives. So the solutions, the general solutions are the translations, and the Lorentz transformations, which is an antisymmetric tensor times the coordinate X in Cartesian coordinates, or in Minkowski coordinates. So and these vectors, they're labeled by the A and B's, which are labeled by some index structure A. So these A, B are just labeled both A and B's. It's not the best notation probably. So there's a Lie bracket between these vectors, which is the standard Lie bracket of vectors, and generates a new vector. So there is an algebra of these vectors. And this is the Poincare algebra, of course. But this is very special for Minkowski. So there are two other maximally symmetric spacetimes. There is ADS4 until the sitter in 4 dimensions and the sitter in 4 dimensions. And just to mention it, because they are relevant for string theory, this ADS4 has a symmetry group SO 2,3. DS is SO 1,4. And there is a reduction if you send the length scale of this spacetime to infinity, you get back to Poincare. The symmetry group of Schwarzschild, the Schwarzschild black hole, there is a spherical symmetry and there is a time translation. And for Kerr, the spherical symmetry is broken to SO2. There's still a discrete symmetry remaining, which is not part of this infinitesimal transformation, but is worth to mention. There's a T-phi reversal symmetry. Okay, so all this is very special to very symmetric spacetimes, but now we don't have a symmetric spacetime at all. So we need something more general than that. But already for killing vectors, there is a special property which would be very useful later on, and it's this one. So a killing vector obeys this property. So if you take this convention of commuting the current derivative, it gives you a Riemann tensor. So this is the standard Misner-Thorne-Wheeler-Wald convention. So try to use this relation to prove that the killing vector obeys this. So you can try it now. and let you think a little bit more. Try to write this down several times with different indices. Try to rotate the indices and write it down several times. All right, I think I will just show you because either you see it or you don't see it. So you start with the killing equation, and you act with the dA. So now you can exchange the last two. You can commute the last two derivatives. So you have these terms. So these two are equivalent to just dA dC, and here you use this property of the Riemann. Now you actually use this equation 3 times. You make a cyclic rotation of the indices A, B, C. So the A becomes C, B becomes A, and C becomes B. And you make it this rotation 1 time. Then you make again the same rotation. So you have the 3 equations. You can cross-check that the indices are correct here. And then you do 1 minus 2 plus 3. So that's the trick, because you see that now that with the 1 minus 2, this term cancels that term cancels that term, and these two add up. So at the end you have 2D, and then you have a combination of the Riemann. So this Riemann minus plus this Riemann. So I just rewrote it here by exchanging a little bit the indices. So exchange a property of the Riemann, you can exchange the pairs of indices. So the BD and AC indices, you can exchange them. So I exchange them here. Same with that one. I exchange the AD with CB here. And same with that one. I change them. So I put the D at the end. So because we want a D at the end here. So now you have this property that if you symmetrize the first 3 indices of Riemann is 0. So CBA plus BAC plus ACB is 0. So you recognize that these 2 terms here, exactly these 2 terms here, so they are all equal to this minus this one. So 2 minus this one. So I simplify by factor 2, put that one on the right-hand side, and you find this one. So note that the position of indices is very easy to remember here, because you have the natural position A, B, C, and it becomes C, B, A, with a D index at the end, which is contracted. So you can memorize this formula pretty easily. Okay, so now enough about killing vectors. We don't have killing vectors, but we are going to use this property. So we need 2 tools to be able to discuss the general case. So the first tool is the killing transport along a curve. So the killing transport was invented by Kerr in the paper of 69. And the idea is the following. If you have a curve, which will be, in our case, the center of mass of the finite mass object. So a curve, and you have 2 points on that curve, Z and X. And you are given 2 tensor fields at Z, a vector, and then some tensor L at Z. You want to build this pair at any point on the curve. And you want to build it by solving these equations. And this is called the Killing transport. It's a very special set of ordinary differential equations. So you see so x prime is any point on the curve, and v is the tangent vector along the curve. So you see that the first equation gives you an evolution for psi b along the curve, because there is a tangent vector dA. So this is the time d tau d over d lambda of psi, which is sourced by this. And here is an evolution of L, which is sourced by this. So it defines psi A and LAB at every point along the world line. So this equation is trivially obeyed as Z, because if you evaluate this on Z, you find that L is just the gradient of the vector at Z. So it gives you the interpretation of L. LAB of Z is actually the gradient of the vector at Z. And the right-hand side then becomes trivial because of the property we just proved. So if L is the gradient, you see that 2 times the gradient gives you the Riemann tensor times psi. So the equation is trivially obeyed as Z. And moreover, what is built up in this equation is that you see here the evolution of LB is antisymmetric. So a Riemann tensor is antisymmetric in BC. So it means that if at the initial point, the symmetric part was 0. So if LAB was antisymmetric at the initial point, either at Z or any point, then the evolution will keep that property. So it will stay antisymmetric. So it defines these vectors and tensor along the curve, and that one will always be antisymmetric if we start with an antisymmetric one. Okay, so, and the idea would be to start with one which is antisymmetric, of course, and to keep that property. Because that's one tool we need. And then the second tool we need is the bitensors. So there's a nice review on bitensor by Poisson-Vega. I just know that when I was writing the notes, I used the opposite convention for what I will call sigma. So I inverted the 2 endpoints. So be careful if you compare. So the main point here is that although there's no vector which preserves geodesic distances between all pairs of points in a general space-time, there are vectors which preserve geodesic distances from a given world line. So you have to think a bit about this. So the idea is to define now the sinh, so-called sinh function. So it's the 1/2, where the 1/2 is conventional, the square of geodesic distance between x and x prime. So if you have 2 points, this quantity is simply the 1/2 the square of the geodesic distance between 2 points. So this is the definition, 1/2 of the square of the geodesic distance. So you can write it this way. So you take any parameter lambda along the curve, and you integrate this quantity between the 2 values of lambda, and you multiply by the difference of lambda. So this quantity is a constant because it is a geodesic. So, and its constant is 0 or +1 or -1 if you have an affine parameter, but here you can take any parameter. So it's just a constant. So you can just rewrite it this way. And it's invariant under reparametrization of the world line. So the constant is trivial because this does not depend on the constant. And here the constant is cancelled. And if you rescale with A, you see that there is a lambda that will give you an A here. There is a D lambda that will give you an A as well, but there is a D lambda here and here. So the A's cancel. So it's invariant under reparametrizations. So this quantity is a bitensor because it depends on 2 separate space-time points. So it's a scalar with respect to both x and x prime. So once you have this kind of bitensor, you can take derivatives. So I have sigma missing here. You can take current derivative of the sigma with respect to either the first spacetime point or the second. So here we use a convention that for the second spacetime point, it will be with primes, the first one without primes. So I will also use that notation here. So the covariant derivative of sigma with respect to with the A, it will be acting on the first point. And with an A prime, it will be acting on the second point. So you can define this vector or the tensor or a mixed component where you act first on A and then you act on the second point, A prime. So all these are called bitensors. So a special property of bitensor is looking at the coincident limit when these 2 points coincide. So the geodesic distance between one point and another when the 2 points coincide is 0. That's intuitive. Huh? So now what's the coincidence limit of a vector? In fact, it has, so if you look at the coincident limit when 2 points become the same, it has to be 0 because it has to become a tensor. So a tensor, there is no tensor with only one index because you can only build it from the metric at one point. So it has to be 0. So actually any odd number of indices, it has to give you a 0. So now you have to see why in the constant limit you get G here, GB, and in that one actually is minus G. So for that, those ones are non-trivial, we need to prove them. So let's do it as an exercise. This is the definition of Sinch function, which is the geodesic distance between the 2 points, 1.5 square. And to prove these properties, it's easier to proceed this way. So first, vary a little bit the point Z and see that you get this equation. And vary is the similar, if you vary x prime, you will have this equation. And then you can prove the rest. So think a bit about it. Oops.
Sorry, Geoffrey.
Yes.
Maybe after we finish this exercise, could you please summarize a bit these last 3 slides, because I couldn't follow completely. It was a bit too fast for me, and
Okay.
the ideas are totally new.
Yes.
I
Yes.
haven't seen them. I don't know. Maybe if others.
Yes. So I will go back.
Okay.
So maybe I will solve the exercise, and it will make things a bit more clear. At least the technical aspects. Then I will go back.
Yes, it will be useful too for me, I think.
Yes. Okay. Very good. So, well, maybe I'll go back first, and let's try to understand this first better. Okay. So these two tools. So the first one is the killing transport along a curve. So the idea is to define these two tensors along an arbitrary point of a world line, given a vector and an antisymmetric two tensor at one point of the world line. So this is so there are different ways to do transport. You could do transport of this vector using the just transport along the curve, the standard transport, parallel transport. So if you do parallel transport, it means that you use the tangent vector along the curve, and you impose that the left-hand side here is equal to 0. And that defines a new vector along the curve. So that's the one you are familiar with, is the parallel transport. And you can, if you have a bitensor, well, sorry, a tensor with antisymmetric components, and you impose that you parallel transport it. Here, the left-hand side, you would just say equal to 0, and then you parallel transport it. So in this case, the killing transport is different. You put the right-hand side, so you do a different kind of transport, and you source it in a way that is compatible with the killing equation. This is why it's called a killing transport. So in the initial point here, you can see that these equations are compatible with the killing equations, because in the initial point, if I substitute Z here, the VA, the VA contract, but is compatible if LAB is the gradient of the vector. And if you substitute that back here, you see that this equation is compatible with the killing equation from this relationship I wrote down here. So, but now in general, you don't need a global killing vector for doing this construction. It just means that it's inspired by global killing vectors.
Sorry, Geoffrey, is LAB, is the initial value for LAB equal to grad psi, or?
Yes. So in practice, this is what will happen. So you will take the initial value for this value LAB as the gradient of psi at Z. And the fact that it's at any point, it's not going to be a gradient, because you just transport it along a curve. So a gradient has a lot of information. It has information along for the gradients orthogonal to the direction of the world line and parallel to the world line. So what you do just is to have an LAB which is antisymmetric, and that's what is what's coming here. It will become the gradient of psi only if you impose some additional condition of how the vector, how these tensors are defined outside the world line. So this is what is coming next after the second tool. But at this point, since we discuss only on the world line, you cannot discuss how the gradient is defined at a point of the world line orthogonal to the world line. So the only thing that you define at this point on the world line is this L, which is antisymmetric.
So it's the antisymmetric derivative of the psi? Is
No,
it so?
not yet. No, it's not, because it will have components that are normal to the word line. So you cannot say that this is the gradient of xi at this point. It will become the gradient of xi only later on, once you define how you define the gradients outside the word line. But you need a prescription for defining it so that it's true.
The initial value for LAB, you said is grad xi, which is not necessarily antisymmetric.
Yeah. So the initial value, you want to select a xi such that its gradient is antisymmetric at one point.
Okay.
So you would choose the initial point so that you have a gradient antisymmetric at that point. So that's the idea of that is coming here next. So you want to start with one which looks like a killing vector at one point, which always exists. And then what you do is you extend it using killing transport. And then next we will extend it outside the word line as well.
Right.
Okay.
But
So,
it is antisymmetric because the grad xi for a killing vector is antisymmetric.
Yes, grad xi is antisymmetric for killing vector. But here, this is not the killing vector anymore. It's just an arbitrary
just
vector.
at the starting point.
Yes, but just the starting point, it will be antisymmetric at the starting point. So it will be killing vector at one point.
Yes.
You can always find a killing vector at one point. You can define antisymmetric vector at that point. So now the idea of byte tensor is basically, if you understand what is a geodesic distance, well, everything is based on this function, on geodesic distance squared times 1/2. And this is the definition of this function. And it's invariant under reparameterization. And then you can define gradients to define these auxiliary quantities. So I think this part is clear. The definition of singe function, well, you have to accept it. This is the definition. It's the correct definition because it's invariant to the reparameterization. So I hope, so all these two tools indeed are not familiar, for they're more advanced. So let's try to prove these properties. Okay, so this was this exercise. So let me now go to the proof that we arrive to these expressions. Maybe we make things a bit more concrete. So I have now two word lines that differ by the initial point. So there is a z plus delta z, and we want to understand the difference of geodesic distance between these two word lines. Since this function is invariant to the reparameterization, we can choose the parameters that span the same interval. So we can choose this delta lambda to be the same for both word lines. So let's do that because it's simple. So that this factor, which is the difference of parameter delta between the two word lines, remain identical. So the difference of the singe function is given by this delta, and then the integral of the first term, and so the difference is when you vary, you have to vary everything can be varied to compute this difference. So there are two things that you can vary. You can vary the metric, and you vary the y here inside. So here you have two terms. Here you only have one, and there's this 1/2 in front. So you have these two terms. So now you can here do an integration by parts of this d lambda. So you have an overall factor, which is a boundary term, and then there is the other term, which is a two derivative acting on the y, because this one does not. If you apply d lambda, well, it's a covariant derivative acting on the x's, which is 0 because it's a metric. So it only acts on the y. So you have this term, and that term is in fact a Christoffel symbol because it's a derivative of the metric. And so here you should recognize the geodesic equation. And so this one is 0. So the only term is a boundary term. So the finite difference is given by this delta lambda, and then times g, this derivative, the delta evaluated. So in this case, it's the initial point that varies. So there's no contribution from this boundary. So there's just this one. So there's a minus sign. So it's evaluated as z is given by this. And if you vary the second point, the final point, you get the contribution from the upper side. So you get a plus sign. Okay, so that's the proof of these two expressions. So now if you take a gradient of the initial point, this is the infinitesimal version of this. So you divide by delta z on this side, basically. And so lambda a is just given by this expression. Okay. So once you have this, it's very easy because now you can just compute GAB acting on sigma A, sigma B. The metrics all combine because it's an inverse metric. So the three metrics combine to a single metric, and then it contracts Z and Z. And the minus sign is squared to 1, and that interval is squared. This one is just the 9 elements, so it's an epsilon. And so together, you see sigma is actually 1/2 epsilon, the interval squared. So this is actually 2 times sigma. And so once you have this, you can take a covariant derivative of this. So on both sides, you act with the gradient. On the left, you get 2 times, well, you have an extra C index now because you act with the gradient, and you can act both on sigma A and sigma B. And on the right, you have a gradient here. So you can raise the index G here. So you get this one. You simplify by a factor of 2. So you can factor out the sigma. So you have this expression. So this is 0. So if you substitute the definition of sigma A, which is this interval, and you substitute it into it, and you get this expression, which is valid in general. So in the coincidence limit, you can ignore the fact that there was this delta lambda that goes to 0 because it has to be true in general. So the coincidence limit has to match with the metric. So this is how you prove this expression. You can play the same game for the mixed index, and because there is a sign difference, there is a minus sign difference, and you get a minus. I'm not going to explain that one in detail. Okay, so it proves these coincidence limits that we will need, these two ones. Okay, so now we arrive to the definition of a generalized scaling vector, and that definition is due to Art 2008. So now we need to talk about how we extend a vector that we can transport here along lambda outside of the curve. So we define a foliation around the curve. So foliation is a set of hypersurfaces that cross the line. So now we are given a pair along the curve, which we built earlier, and we define the vector in the vicinity of the curve by using the fact that the geodesic distance is left invariant. So we want to define a vector that leaves invariant all the points with respect to that raw line. So this is the statement that I said before. There's no killing vector in general that leaves invariant the geodesic distance between arbitrary set of points, but there is a vector that you can build that keeps all geodesic distance invariant under between one particular raw line. So is this exactly this equation? So for any point that intersects that is in the intersection of the foliation with the word line, and any point x prime on the foliation, you want this geodetic distance to be preserved. And the proof that it exists is the following, because I just state that this is the definition, but you have to prove that it exists. If you act with the current derivative, you can commute with the Lie derivative here, because everything is a tensor with respect to the first indices. So it's also true that you have this equation. So now if you express the Lie derivative, it's a derivative. It's a derivative, and then it also acts on the various indices. So you Lie drag both the points, the first point, and you Lie drag the second point. So that's this second terms, and there is this index here. So you also have this mixed tensor type term. So the total Lie derivative is this one. So if you rewrite the first term on the left-hand side and the other terms on the right-hand side, you have this equation. And now you define the inverse such that you have this. So you define an inverse of this derivative of sigma A. So if you think about it, this inverse always exists locally, but it does not exist globally. So, but if you are very close to a word line, you can always define this inverse. I'm not sure I want to explain why it's not true globally, but yeah, basically, if you have caustics, you cannot invert this. Caustics means that you have two geodesics that will end up on a single point. And then if you want to inverse the geodetic distance between these two things, you will have to know from which curve you come from. So you have a non-uniqueness of H. But if you are very close to the word line, you can always invert. So if you admit that you have this inverse now, you can multiply each side here with this inverse. And so you find that psi b is equal to this inverse times these two terms. So I rewrote them here. So you get a minus sign coming from this definition here. And so I get these signs here. So it exists because it's written explicitly here. And so if you read it, so on the arbitrary point x prime, it's a combination actually of the vectors on the word line and its gradient on the word line. And this particular combination is given by tensors, these two bitensors, which are given explicitly by this. Okay, so I know it's a bit technical, but that's the key equation that I needed to derive. So this is the equation we just derived, huh? And this is the relationship, these two relationships that, so the inverse relationship, and this is the definition of these bitensors. So equivalently, I claim now I can replace it with the LAB that I defined earlier. So I claim that I can just make that replacement. And you can see that it's correct by doing the coincident limit. So if I take z going to x prime, now the coincident limit, we already proved this one. That was the exercise. So if you take the coincident limit of this equation, and you see that that one is a minus delta, it means that this one has to be a delta by consistency. We proved this one already earlier, and we proved that one earlier. So now if you take the constant limit here, you see that one we just proved it was a delta. This one we proved it was a delta, so it's a metric. And that one, well, the constant limit of the sigma A is 0, so it's 0. So the constant, if you take the constant limit here, you find that this term cancels and that one becomes a delta. So psi x is psi. Okay, you recover the correct definition. And you have to find now that you find this definition. So you compute the gradient of psi. So here's the gradient. So you compute it with respect to the index x prime. So the only x prime appears here and here. So you get this equation. And now you take the coincident limit. So since you have this, the gradient will kill the metric. So the constant limit is 0. Again, there's only one index, so the constant limit is 0. And so now for that one, you have to be a bit careful. So if you write with the constant limit here, the one of h will give you 0, but if the gradient acts on the sigma, it gives you a sigma AB prime, which is non-zero. So these two terms combine. So this one at the end gives you a delta, and you get this equation. So it's true that you can replace it, because it just works in the constant limit, and then all the rest follows from the definition of the dragging here from this construction. So now we saw that if we start with at the initial point with if we choose from initial point on the word line the psi to be to have a gradient which is antisymmetric, it means that everywhere on the word line L will be antisymmetric. And since now we have this construction, we can take the antisymmetric part of psi here. So that's the final step, is to bring this antisymmetry here. So it's a bit technical, but we arrived to the main results. So now we built a generalized Killing vector for an arbitrary curved metric, starting from a Killing vector at one point. And that's the final result. So you can check that the Killing vector of Minkowski spacetime are, as a particular case, obey this equation. So it's very easy to see. And since it's a bit, yeah, maybe you feel uncomfortable with these definitions, maybe I should do the exercise myself. So you have to see that Minkowski spacetime, you have exactly these equations. So it's very easy actually to check, because in Minkowski spacetime, a global Killing vector is given by these equations. So if you write them in a different point, you have these equations here. So you can actually rewrite this as x, replacing the x prime by z with this difference, right? So you can rewrite this one as this. You can write a Killing vector at one point as the Killing vector at another point plus x prime minus z times the b, and b is actually the gradient at that point. So the global Killing vectors of Minkowski obey this equation, and you see that this equation is actually the same as this one, where you substitute these bytensors in this way. So you see that this is another way to think about the Killing vector of Minkowski spacetime. You can, once you know them at one point, and you know its gradient at one point, you can reconstruct them everywhere by using this method. Now the point is that this is true without any global symmetries. You just need to know these vectors at one point, and you can reconstruct, you can construct a psi everywhere without any global Killing vector. So this is why it's a generalized notion. Okay, so now that we have that tool, you can build actually your charges. So if you have a body with a stress energy tensor, you now can build these quantities in general. So you have a generalized Killing vector, and you integrate it with the stress tensor of the body, and that defines on this given hypersurface that crosses the wall line of the center of mass of the body. That gives you a conserve, well, not conserve, but that gives you a quantity, PT. So this is the quantity we were looking for. And now, because of the way this vector was built, so it was built starting from psi and its gradient at one point on the word line. So we have a decomposition of this quantity. So if you substitute this inside of the definition of the, so this is called a generalized momentum, of this generalized momentum. So you put it inside, you get, you can factor out this psi, evaluate it on the specific point on the wall line at fixed time on which you evaluate this, plus its gradient. And the overall quantity in front are just given by these expressions, right? Is the integral of the body integrated with this kind of weight, and the other one is integrated with the other weights. So the only integral is over x prime. So all x prime appears here. So the interpretation of these things. So this is the momentum vector with respect to the reference wall line at foliation time t, and that one is the Lorentz charge tensor with respect to the reference wall line at the foliation time t. So we define and generalize these generalized quantities. So now we are ready to derive the equations of motion. So we have a current, which is this body stress tensor times psi. So that current, if you take the gradient, is given, so since the stress energy tensor is conserved, it's only acting on psi. So, and this is symmetric. So it's 1/2 the Lie derivative, which is 2 times, that one plus is a symmetric part. So you have this quantity. So if you now use Stokes' theorem in the usual way, so you take an integral over the volume of this divergence. So it's equal to the gradient of when you put the screw inside. So and that one is equal to the boundary of the volume. So if I write this down explicitly, I replace now this gradient of J with this part. So I get this equation on the left side. So volume integral and time integral of this. And on the right hand side, if I take a volume that is bigger than your object, there is no stress tensor here. Only the stress tensor is the difference of times here. So you will get the momentum, generalized momentum at time t minus the generalized momentum at time s. So infinitesimally, if you take infinitesimal interval, you arrive to the equation that the time derivative of the momentum is equal to this integral. So this is a generalized force. And this generalized force arises because of the failure to have a generalized killing field. So these are the internal stresses of your body. So now the claim is that these are the equations that we are looking for, the Mathisson-Papapetrou-Dixon equations. So I will just rewrite the equations now here. And now it's very easy to write down final equations. So we know that the momenta are given by a combination of these generalized killing fields at the point of the wall line, where with the overall factor, which are these special these momenta and Lorentz charges. So I just substitute that in on the left hand side. So I take the time derivative. So the time derivative, the time here acts on can act on the p, and it gives me that term. So it's a total complete time derivative because there's an implicit and a time dependence and a dependence on the position as well. And there is another second term, which is the position here, the psi on the z. So you can take a derivative with respect to the coordinates, and then derivative of the coordinate with respect to t. So time derivative of the coordinates. And now, since this one is chosen to be anti-symmetric on the wall line, I can put the anti-symmetry here. And then you have the similar terms here on these ones. So you have a dt here, and on that one you can also compute the derivative along time. So it gives you these terms. Now, because that one has been built on the wall line using the killing transport, and this is where this killing transport is important. So this equation reduces to this one. So I can just replace it with the Riemann tensor here. And on the right-hand side, you can make the similar decomposition of something proportional to psi to the gradient of psi. So so this is true independently for these vectors and the antisymmetric parts. Oops, you arrive to these equations. So these equations are called the Mathisson-Papapetrou-Dixon equations. So they arise because these generalized Killing vector, which are purely translational at one point, it becomes a combination of translations and Lorentz transformation at a later time under Killing transport. So it gives you a mixing of momenta and Lorentz charges. So I find it very intuitive that there is this mixing because of the mixing of the nature of this generalized Killing vector. So note that the final variable to describe the motion is a momentum, the spin or generalized Lorentz charges, and the word line velocity, v. And now we have many extra variables that could describe this force and torques here.
Can I ask a question?
Yes.
When we use these Killing vector properties that grad C, grad A, Xb equal the Riemann tensor, yes. This is only valid for the Killing vectors, but
yes,
we have these extended Killing vectors.
Yes.
How do we know
Yes.
that it's respected for the point that we want to use
Yes.
it?
So yeah, so the step here is that you replace, so here, the point is that this gradient here at z is equal to L ABZ. So is is basically this proof here.
Yeah.
So I should really write, so these two things are equivalent because of this property here that they coincide, which we prove here. So I should really put LAB in this definition. So I didn't update the slides there, but I should really put LAB. So now if you put LAB, it's really an LAB everywhere here. So when you are at this step, you have a gradient of LAB along the word line. So now you can see that is exactly the equation of Killing transport that I wrote down here.
Yes, okay.
So you have this equation here. So the gradient of LAB is given by the Riemann.
Because this ZT is along the word line, it's not outside.
Because it's along the word line, because this is an evolution along the word line only. Because it's, yeah, exactly. It's just along the word line at that point. But yeah, I should have better written, but since they're equivalent, you can write one or the other.
Yes.
But so yeah, now you see, huh? So I'm here, yes. So here, yeah, if you see it as an LAB, now you use the Killing transport property. So that was a key here to use to obtain these equations. So it's the key to build these generalized Killing vectors.
Yes. Thank you.
Just a question.
Yes.
Are there as many generalized Killing vectors as Killing vectors? Like, because
yes, so indeed. So that's a very good question. So if you want to know at one point how many Killing vectors you can define at one point, well, it cannot exceed the number of Killing vectors that you can build. So it's 10. There's no more. So it's exactly the same number.
Okay, thank you.
So you have 10 generalized Killing vectors. Because that you see, you have to start from one point, and at that point you can build only 10 generators.
Thank you.
Yeah, so the basis is you need a basis at one point. There's no, you have 4 quantities here. I mean, that's the best you can have. Huh? At one point is four numbers and an antisymmetric matrix, which is 6. So it's 4 plus 6, it's 10. There's no extra numbers you can put in.
Sorry, can you go back to the definition of this little p and s? Yes, here. So the integral is over. Can you remind me what is the integral over?
Over the entire, over an hypersurface that cuts the body. It cuts the body at fixed time.
Okay. Yes.
It's a slice at fixed time that slice the body. So it's the
Yes. Okay.
okay. So now let's go for the properties. So all the hard part is over. Let's go to the properties now. So if we have a background killing vector, and we are lucky to have one, so this is the case for Kerr, actually, there are background killing vectors. Huh? So now this least derivative of psi will always be 0. So then it means that these generalized quantities will be exactly conserved. So these quantities are given by this. So it's this particular combination of the momenta and of the Lorentz charges. So these two quantities, so Kerr has two killing vectors, so there will be two conserved quantities. As for geodesics, you are familiar with this one, actually. If you remember, if you have a killing vector, the global killing vector times the momentum is conserved on the motion. So from this construction, you directly see that the generalized momentum, which is given by the sum of these two quantities, is also conserved. So now, if you look at these equations, there are 4 equations here. Here is antisymmetric, so you have 6 equations, but you have well, too many variables because you also have the z dots. So you have 4 extra quantities. So you are missing 4 equations to close the system. So to fix this, you need to fix what you mean by the center of mass. So those are called spin supplementary conditions. And there's 2 standard options. The one done by this author, which I cannot pronounce because it's Polish, something like Tulciev, but I'm not sure. So you impose that this tensor is orthogonal to P. The one imposed by Mathisson originally is that it's also covariant, and is this one. This one seems preferred in the literature because it identically chooses a raw line. Well, that one does not, it seems. So we'll use this one. So now the system is closed. One property is that if you choose the proper time, you can solve for the velocity in terms of the rests. So there's a general proof, including all the torques and everything, these forces and torques, but it's very nasty to write it down. Something important is that once you have imposed that condition, you can define intrinsic angular momentum this way, because you can reduce the number of degrees of freedom into a single spin vector here. And you see, because now you see that well, it's because of this orthogonality condition that it makes sense to define this. And you can also define the mass in this fashion. And you have to check if it's conserved or not, so that's not trivial. We'll discuss that in a minute. And the spin length is naturally defined as the square of this. And the fact that this is conserved is also not trivial to see. So now let's...
Sorry.
Yes?
Sorry, this intrinsic angular momentum is as opposed to like orbital angular momentum? I mean, is there a notion of total angular momentum, or?
Well, no, this really yeah, I don't want to make any difference at this point. Is maybe it's just total angular momentum of the system. Yeah, okay. Maybe I should not say intrinsic. It's just the total angular momentum.
I see. And are we assuming any killing vector at this stage or no?
No.
Okay.
You don't need to assume any killing vectors. This is defined independently.
Yes.
So generalized killing vectors are built for any metric. That's really the beauty of it. Huh? So now you can show that this Mathisson-Papapetrou equation using this Tulciev condition can be used to solve for the velocity. So, and this is the explicit expression that you can find. That was derived by Ehlers and Rudolph in '77. So we can try to, we can go into the proof of this. So it's not that easy to prove. It takes a bit of time. How am I going with time? So I have only 8 minutes left. So let me go through the proof directly. If I let you work on it, it will take much more time. So I give you a hint of how to prove this. So the idea is to resolve, since you have an over-constrained system now, with that one, it becomes just constrained enough. And you actually algebraically solve for V in terms of PNS, and then you have differential equations for PNS. So how do you prove this? So you start from the Mathisson-Papapetrou equations, and you take the time derivative of this spin supplementary condition. So if you expand this, there will be either you take the time derivative of S or of P, and then you use these equations. So, and then you have to work out a little bit. So from acting on the S, you get these terms. So it's algebraic in terms of P, V, and P. So, and you have two terms because there's antisymmetric. So there's in particular one term where you have the V index is 3, where you have a VA index 3. So you put that one on the left-hand side and all the rest on the right-hand side. So this is what you find. So you see that V is as a tensor as the proportion to PA with some normalization, which is given by this. And there is some term here, which is V times something, which I call BF, which is this tensor structure. So we solve for n later, but we first want to understand how to solve this. So you see that the V appears both in n, which we'll solve for later, and it appears here on the right-hand side. So we want now to solve for V. And the way to do is to replace V inside of the right-hand side. So you just replace again V inside of the right-hand side. You get the first term is still there, and you replace the V here, so you get this term, and then you have the B contracted 2 times. And now you have to understand this, how the 2 B's contract. So how the 2 B's contract, you have to understand what's the property of the Riemann with the S's. So that's a bit tricky. But if you, as I told you, from here, you can actually write S as a specific, in terms of a spin vector, which is orthogonal to P. And from there, you can deduce this property. So if you act with epsilon on A, B indices here and on the C index here. So now you substitute S with this. So you have a bunch of epsilons. You have 3 epsilons that you have to contract. But since you have only, well, we first have to contract the first one. Yeah, just the first one, actually. The first one. So you have 2 epsilons to contract. But you have P and S here. So it will be a combination, antisymmetric combination of P and S contracted with the S here. So the only thing that can happen is that. But now, since P is orthogonal to S, is 0, and since S is orthogonal to SCD, it's also 0. Now if you contract the S here, it's antisymmetric, it's 0. So you find 0 here. So the conclusion is this is true. And now you contract this with the Riemann, and you use that property, and you have to work a little bit, and you arrive to this expression. So you can replace the Riemann contracted in this way. And if you now, so the proof is a bit long, but now if you work out how you do this product, you find exactly this combination that you have to replace, and then you find that you can actually replace it with the B F VF with an overall factor, which is actually the trace of B. So once you do that, you replace here with the trace of B, and you keep iterating. So you will always find the same thing with an iteration over the trace of B here divided by 2. And that sum is an infinite sum, and the infinite sum here is actually 1 over 1 minus the factor. So that's a standard relationship for this sum. And this is the solution, because now V is a function of P only. And now if you normalize the time to be a time like geodesic, so the V normalized to be the proper time, this is -1, you can solve for n. And you arrive to this guy. So it's not that hard, it's a bit technical, but it's possible to do. Note that there is another normalization of time in the literature, which is given by this one. So different normalization, and gives as a result another n. And I don't know why. Yeah, sometimes it's preferred in the literature. So now another exercise to see with these equations, because now you know that V is expressed this way. You can prove now that the mass and the spin are conserved. And actually that proof is very easy. You want to prove the spin is conserved, so you want to act with the time derivative on this. So you want to prove that this is 0. And so this actually is, this spin here is P's contracted with V's. And now you replace the V with this explicit expression. So the P part is trivially cancelled here. So you're only left with the P contracted with, this one. And now you have to, work a little bit here to see that you are just left with this P is actually contracted with your Riemann here. So you arrive to this equation, which is trivially 0. And to prove that the mass is conserved, so it's a similar equation here. And you replace dP by the expression, and you replace P by this expression. So you have to invert this. Well, the easiest way maybe is just to replace dP in terms of V, and then replace V with this one, sorry. And then you have to see that you have a square, which is again 0, where X is this. So that's the way you prove it. The easiest way, probably. And then in the last minute, so we arrive to the most interesting part. So to be able to derive gravitational waves from this system, you need to know the stress energy tensor. And so the initial approach of Mathisson was to reduce the stress energy tensor to its lowest multiples moments on the world line. So here we have deduced the Mathisson-Papapetrou equations. Now we want to finalize and reduce the stress energy tensor to its lowest multiple moments, which is a function of this P and S, which is this lowest variable, P, S, and V. And the answer actually is given by this. So the first term looks like the one for the mass, the monopole, except that now there's a P and V here. Instead of being a V and V, it's P and V. And you have a derivative of your delta function. So this is a stress tensor defined on the world line in terms of simply in terms of distributions. So when Mathisson wrote something like this, but the theory of distribution was not yet invented. Actually, it was invented only later on, when there was this famous paper of Schwartz in the 50s. So it was re-understood in terms of distribution by Tutchev in 59, and in its final form, it was written by Dixon. So now, an exercise here is to prove that the conservation of this stress tensor is equivalent to the Mathisson-Papapetrou equation, to see that this is actually the skeletonization, the reduction really on the world line of these lowest multiples. And it took me a while to understand how to do this. So the simplest way, and I got this from Arte, is to use an arbitrary test vector to prove this. So maybe just do the proof in one slide. So if you take a test vector and you look at this term, so this is 0 because of the type of divergence. It gives you only boundary terms, and you are looking, you ignore the terms at infinity. So it's just 0. So you have two terms, the one acting on divergence and the one acting on the vector. So proving conservation of the stress tensor, proving that this term is 0, is actually equivalent to proving that this term is 0. And that term is very easy because there is integration now that will kill all the delta functions. So this integral, once you substitute these delta functions, will give you this. And now you use very simple properties. So you can always decompose something into symmetric part and anti-symmetric part. So you can do the reverse, replace the symmetric part with this anti-symmetric part and this contraction, these vectors. If you have an expression like this one, since S is anti-symmetric, you get an anti-symmetry here, so you get a Riemann tensor with the 1/2. And if you have a vector contracted with derivatives, it's actually the definition of the covariant derivative along the word line. So now with these simple manipulations, you can rewrite this in terms of these combinations. So here you recognize the Mathisson-Papapetrou equations. And in fact, they are totally equivalent to Mathisson-Papapetrou because these two terms are independent of each other on the word line. And one way to see it is that they're independent. That was confusing me a bit, but it's true because once you define you define another phi by adding a gradient, this one remains unchanged. So these terms definitely you can fix them to 0, and you can choose this gradient to choose these vectors as you want, because if you take, for example, coordinates along the word line that are normal, you can define 4 different functions on the word line. So independently, you can fix these two. So equivalence, that's proved equivalence of this conservation with the Mathisson-Papapetrou equations. So do you have questions on this before the break?
Yeah, I have a question, but it's about a few slides before. When we define the general momentum and the angular momentum, P and S.
Yes.
It's an interpretation of this value, or is there really momentum and angular momentum in the sense of like algebra or some other properties?
Yes, so it's indeed, at this point, is an interpretation. Right, so yeah, it's a good question. So they obey these equations. So yes, so there is some ambiguity in what you mean by angular momentum always. So the ambiguity is fixed here with this condition. So depending on how you fix this, the physical interpretation changes.
Yes.
So this one S now is an angular momentum with respect to the center of mass given by this condition. Because it's a spatial, it's a spatial vector. The V, yeah, the fact that there is this non-trivial relationship between the momentum and velocity makes the interpretation a bit unclear. Okay. So one has to be careful in what we mean. The fact that there is this spin vector which is conserved and the mass which is conserved are two very nice properties. So maybe this is why you have the interpretation. This is a time-like type vector with something which is conserved, and so that one independently is conserved, and this gives the interpretation of spin and mass.
Okay, but it's just like how they look. It's not strictly speaking momentum. We need to work more to check if they obey some algebra or anything.
But yeah, so in terms of algebra, I'm not sure how you define an algebra of these two, of P and S. Because those are integrals, they're defined as as integrals. They're not vectors. I mean, for the algebra of vectors, you have a Lie bracket, but here these p's are really defined as spatial integrals. So their definition is here. Huh? So I'm not sure how you would define an algebra of these quantities. But I see what you mean. Huh? Maybe there is a way to define an algebra, but I don't know how you would define it. Yeah, so you will have to define a Poisson bracket, some bracket between these two things. Yes, you are right. There is a definition of bracket that exists, which is acting on the position by acting with the vector associated with the. Yeah, so I guess the Poisson bracket between them can be defined by acting on the definition here with the associated vectors. Well, but for this vector, I'm not sure how you would define this action. Okay, I will have to look in the literature to see a definition of Poisson bracket.
Thank you.
Sorry, another question. So you showed that these Papapetrou equations are can be derived from the conservation of this stress tensor, but is there an action from which we can derive these equations?
Yes. So there are actions. I didn't read all the literature in that, but there are actions. You need to introduce additional fields to write down this action. So in addition to your tetrads, you have to work with tetrads, and you need to work with some spin. So the appropriate variable, the Cartan calculus.
Right.
Then you can write down an action.
Do you know originally how are they derived? Is it from this stress tensor?
So these Papapetrou equations were derived from not from an action principle, and they were really derived from conservation of stress energy tensor.
Okay.
But so the way it's written in the, for example, in the Blanchet review is derived from an action, but the action is derived with a lot of hypotheses on how you have to write down something which is gauge invariant, which is then you have to use frames. You need extra ingredients to derive this action. Here, the way I did it in this class is using these generalized scaling fields and the stress energy tensor only. And you need different types of ingredients to derive from the action. You don't need the generalized scaling fields, but you need to introduce auxiliary fields.
I see. Thank you.
Okay, and so I have maybe another element to answer the first question about why it is called momentum and linear and angular momentum. This is what Harter is saying is that if you take the flat limit of those two quantities, you recover exactly, in fact, what you would define as the linear and the angular momentum of an extended body, actually. Yes, so basically, in his paper, this is really the reason why he called them the linear momentum and the angular momentum.
Yes, so that can be seen directly from this expression, because for flat space, you see here and here, these two quantities are written here. So there's a delta and x prime minus z, and you see directly that this is the standard definition of momentum and spin. But now that if you're not in flat space,
no, it breaks. But
the interpretation becomes more complicated. Yeah. Okay, I think we should break for a couple of minutes. The break for five minutes or so, and then I will go to the final, which is totally independent chapter on quasi-normal modes. Yeah, I wanted to say here, but this is not very important. Some remarks. So if you look at the quadrupole and higher multiples, they're not constrained by the stress tensor conservation, just by the dynamics. It's just interesting to know that this system is chaotic in Schwarzschild Kerr, contrary to geodesic motion. So geodesic motion, there are just enough conserved quantities to have first order equations, and therefore non-chaotic system. But for spinning particles, there are more equations than conserved quantities, and you have chaos.
So the motion of Earth is chaotic.
Ah, well, that's the three-body problem. Yeah, the three-body problem in Newton theory is chaotic, but here is just about the two-body problem.
I mean, if you only consider Earth and the Sun, because Earth is spinning and is an extended object, then
yes, that's also right. Yes.
Okay.
Yes, there's a lot of chaos actually in the solar system that is on astronomical scales because of it's an n-body problem. So if you look at the trajectories, they are chaotic actually. Okay, so let's break 5 minutes. All right. Let's restart. Okay, so the last part is about quasi-normal modes. So far, this quasi-normal modes has not been observed, but with more accurate detectors coming, in particular with LISA, also in space, it will be able to. Well, we will be able to measure this as quasi-normal modes, and they are very important because of the uniqueness of the Kerr metric. So if you access these quasi-normal modes, you have direct access to these Kerr parameters, and you can check the validity of general relativity. So let's discuss that. So in the late stages of merger, after the ring down, so here is an example of some neutron star merging. In this late merger, the two neutron stars collide into a black hole, and that black hole then has a ring down behavior. So it's like a perturbed object, and that perturbed object just radiates with a very specific modes, like that I will explain in a minute. And then at very, very late stages, you have the so-called power law tail, which is usually too faint to be observed. So here I will look at the late, but not that late stage, which is called a ring down. So in that ring down, there are specific frequencies, which are the quasi-normal modes, and specific amplitudes of each frequency. So these amplitudes are a function of the binary source parameters, and they are not universal, and they are hard to calculate. But the frequencies are a function of just the mass and angular momentum of the final black hole. So the main, to compute these frequencies, the main tool is the Tukowski equation, which was derived by Tukowski in 1972, based on earlier work by Penrose and Newman. So I will explain that in this lecture. For the amplitudes, it's a different story, and the estimates, but they require numerical methods. And so there was a famous estimate by Flanagan Hughes in '97, which I will not explain. I will concentrate on the frequencies. So the plan is to start with the Newman-Penrose formalism. And we'll need as well the Petrov classification of the Weig tensor. And from there, we'll arrive to Tukowski decomposition of linear Kerr perturbation and how to solve them. So that's the plan. So what is this Newman-Penrose formalism? The idea is to decompose the metric at any point using a tetrad. So at any point, you define a basis of 4 vectors. And at any point, you have the tangent vector of your manifold is a Minkowski spacetime. So at each point, you have a Minkowski tangent spacetime and 4 vectors, and you can reconstruct the metric this way. You contract your vectors with the Minkowski metric. So this vector has one index in the tangent space and one index in the spacetime, mu. So you can these tetrads, called tetrads, they are useful for the so-called Cartan formalism, where you replace your, instead of having metrics as your fundamental variable, you have instead these one forms, which are called the fundamental one forms. And you can reformulate Einstein's equation using that and using their derivatives, which are called the spin coefficients. They're also useful, etc., to describe fermions propagating in spacetime, because you cannot couple fermions to the metric. You have to couple them to the tetrads. But for this class, the importance of these tetrads, well, is to choose these tetrads in a very specific way to describe gravitational radiation. So the Newman-Penrose formalism is a specific choice of tetrads, which are complex, and where the tangent Minkowski metric is chosen at each point to be this one. So two null directions, because you have two zeros here, and this complex basis for describing the other directions. So you have 4 null vectors in total. So of course you have null vectors in the space-like direction, so this is why they are complex, these two ones. So they're called L, N, and M bar. So the metric, if you use this property, and you have these 4 vectors, so these 4 vectors are the 4 E's here, and you contract them here until you find minus L N minus N L plus M bar plus M bar M. So this is your metric. So now you replace your metric with 4 null vectors, with the data of 4 null vectors at every space-time point. And the fact that it has null directions is suitable to study gravitational wave propagation, which goes along the line cone in null directions. So in this reformulation, you, instead of having covariant derivatives, now you want to have covariant derivative along each of these 4 vectors. So you define special symbols for them. So D for L, for N you define delta, and for M you define a small delta and small delta bar, which is this complex conjugate. You want to replace the Christoffel symbols. So you have in total you have a 4 times antisymmetric part of symmetric part of this, which is 6. So you have 24 Christoffel symbols. So these Christoffel symbols, well, you have to replace them with the various covariant derivatives of your tetrad, and so you have these 12 coefficients and their complex conjugate. Well, because they are complex. So that looks very messy because you need all these variables. So instead of having something nice like gamma, but that's the way it works. And now to reformulate the curvature, so instead of having 20 components of your Riemann tensor or 10 of your Ricci tensor, well, so you are looking, we look mainly at the Weil tensor. So the Weil tensor is the traceless part of the Riemann. So you remove all the information about the Ricci, and you look at the component independent of the Ricci of this part. So if you this is a special combination which isolates these 10 degrees of freedom, which are independent from the Ricci. It's called the Weil tensor. So you want to reformulate this part, the Weil tensor part. So there are these 10 components. So you can contract with suitable combination of these tetrads, and you find 5 complex scalars, which are called the Weil Newman-Penrose scalars. So, and the Ricci also, you can contract them with some suitable combination. You find 5 extra curvature scalars, but we will not use them here. So now let's reformulate gauge invariance. So in the original formulation of gravity and the metric, that there is diffeomorphism invariance. So here all these are contractions, so they are scalars. So there's not any more diffeomorphism that acts on them, but they depend upon the choice of tetrads. So this choice of tetrads, let's discuss about it. So we want to preserve the fact that there is a metric exactly given by that. But there are many ways you can exchange these components to preserve this metric. So an obvious way is that you can exchange L and N, and it will obviously not change anything here. So that's one example, but then you have also continuous examples. And if you can list them, so instead you have this flip, and you have local, so you can do actually anything that is a local Lorentz transformation. So naturally, since you have a metric, you have such a metric, you want to consider all possible rotations that preserve that metric. And so it's a Lorentz transformation. So a Lorentz transformation is parameterized by 6 real numbers or 3 complex numbers. So the first complex number gives you what is called rotation of type 1. It leaves L unchanged. It rotates N, M, and M bar in the following ways with a complex number. And the rotation of type 2 keeps N unchanged and rotates L, M, and M bar. There's a bar here missing. And then rotation of type 3, it leaves the rotation L and N unchanged, but change the overall scaling and performs a rotation of M. So there's these 6 Greenwich functions because you do a Lorentz transformation of the tangent space metric. So that's the general transformation you can do. So let's do an exercise to get familiar a bit with this formalism. So here's the definition of the 5 components of the Weil tensor. Now prove that under a rotation of type 1, which is that type of rotation, these Weil tensor transform this way. You can do the same with the type 2, and you have this transformation law. And for the type 3, you have this transformation law. So I'll let you exercise yourself a little bit to get familiar with this formalism. Okay, I think I should move forward. It's a question of substituting and getting used a bit to the notation. So I don't think there's much more to say than just working out the substitutions. And another one is to prove that if you have now if you define these three antisymmetric bivectors, which are given by these ones, very specific combination of bivectors, you can prove that the y tensor is a linear combination of these three bivectors in the following way. So this is a very nice property because it allows you to reconstruct the y tensor from the five Weil-Newman-Penrose coefficients here. So there's a way to prove this is to well, apply the act with the various components. So all of these ones are independent of each other. So you just need to recover these individual coefficients by contracting. So here, if you contract the left-hand side with L, M, L, M, you have to prove that all this is zero. All the other terms give you zero. And you have to see that by explicitly computing them. That requires a little bit of time. But this is a notion of pure algebra, just contracting them and just seeing that you get exactly zero with the right contractions. So I don't think I should also spend too much time on this. So if you accept this, so you see actually maybe I can leave you a couple of minutes to try, but the easiest way is to compute these terms, because here you see that you have the combination LM appears here in these sets of indices, either the last set or the first set, and here you have a combination M bar N that appears in the last set or in the first set. This is just antisymmetric, but you can put it the other way. Huh? This is antisymmetric. So if you contract this expression with LM, you only need to know how to contract either of these X, Y, and Z with this LM. And if you contract with M bar N, you only also need these expressions. So you are already halfway through proving these equations. So it's the simplest way to first start to compute this. So if you want to do it at home to check, first check this one and then act with LM. And then to find either these three coefficients, you act either with LM, LN, or M bar N in addition to the right side. And then you will be able to prove the quality on this side as psi I equals psi I. Okay. Now, another exercise. If you now know that the y tensor is given by this, you can prove that this is also true. That if you contract the Weil on the left here with suitable combination of L with some antisymmetries, all this will disappear. This part will disappear. You will just be left with this part. And the X contracted with the L's will just give you this combination, because the X was just some combination of N and M bar. Then you have to use the properties that you have a metric with some right orthogonality conditions, and you have to arrive to this. And then you have a complex conjugate term on the right here. So let's just accept this formula as well, because we will need it in the following. So now that we have all this formalism, we can do the Petrov classification that was done in 54. Actually, it was done also at ULB here by GNU, who didn't know the work of Petrov, but it was too late. So it was done in a higher dimension only much more recently in 2004. In 4 dimension, it was done 54. So when the Petrov classified the Weil tensor by the number of degenerate local eigenvalues and eigen bivectors of the Weil tensor. So this is the eigenvalue equation. And this classification is useful to understand the type of eigenvalues and eigenvectors you obtain from this equation. So it sounds totally remote from what we want to do, but let's wait and see. So since this Weil tensor is totally independent from the Ricci, it's independent from the Einstein's equations. So this classification is valid both for vacuum solution and non-vacuum solutions. So it's just a universal classification for once you have a metric, it's on the part which is unconstrained by Einstein's equations. So note also that the Weil tensor is conformally invariant. So if you rescale the metric, actually one property of it that is it remains unchanged. So this Weil tensor is identical for ADS and Minkowski. We will not have any information about the difference between these two spacetimes, for example. So now the point is that there are 3 equivalent ways to formulate this classification. So Petrov is the first one, the one I wrote to you. But then in the 60s, it was shown by Penrose that solving this eigenvalue problem is equivalent to classify spacetime according to the degeneracy of principal null directions of the Weil tensor. So these principal null directions are the vectors which obey that equation. So those each vector obeys that equation is called the principal null direction. And Penrose showed that these 2 classifications are related. Yet another independent formulation is the following. So with respect to a chosen tetrad, the Weil tensor is completely determined by the 5 Weil-Newman-Penrose scalars. So, and now you can ask how many of these scalars can be made to vanish for a given spacetime by choosing a suitable orientation of the tetrad frame. So I'm not going to prove that 1 is equivalent to 2, but we start from 3 and we will prove 2. So now we derive from this exercise that you can do at home. You have these 2 type of transformations, and this is that the transformation of the tetrad you can write down. So now let's see, when can you make these 5 vanish, the psi vanish. So given a Newman-Penrose tetrad, you compute the 5 scalars. If all of them vanish, then we're done, because okay, they'll vanish. So let's assume it's not one of them is not vanishing. So we can assume it's psi 4 non-vanishing. Otherwise, you just do a type 3 rotation, and psi 4 will not vanish as a result of the rotation. So we can assume psi 4 is non-vanishing. Now we consider a type 2 rotation with a complex parameter b. And we look at psi 0. So psi 0 vanishes for b if b is a solution of this equation. Now the point is this is a 4th order equation, 4th order polynomial in B. So there are exactly 4 roots. So this is a complex equation with of order 4. So there are 4 roots. So there are the corresponding type 2 rotations. If you see how they act on N and L and M, so they acted like this. So if you look at these, the resulting 4 L vectors, these are 4 special L vectors. And in fact, they correspond to the 4 principal null directions of the Weil tensor. Because from this exercise here that I mentioned, if you prove that this is equal to this, then you see that if psi 0 is 0, it proves that the L corresponding L is a principal null direction. So that's proof 3 goes to 2. So if you have, you determine how many of these scalars, or how many scalars can be made to vanish. Well, actually, here at this point, we only proved that you cancel psi 0. But there will be a higher roots, so actually other psi will also vanish. It will imply a principal null direction can be found. So there is a degeneracy structure of the roots of a Corti polynomial, and that leads to the classification. So here I'm skipping a bit the steps, but if you have a more degenerate roots, additional psi will also have to vanish. So the structure of the roots is very easy. You have either 4 different roots, or you have 2 coincident roots and 2 simple roots, or you can have 2 coincident roots and 2 coincident roots, or you can have 3 coincident roots and 1 root, or 4 coincident, or no roots at all, where all the psi vanish. So that's the trivial case, so the phi vanishes. But if you have only 4 individual roots, psi 0 vanishes. If you have a double root, you can prove that psi 1 also vanishes. If you have 2 double roots like this, still only phi 1 vanishes. But if you have 3, you have this one, and 4, this one. And this I didn't prove, but you have to check the proof for the equality with number 1 and 2. And you can see that this condition, this degenerate null direction, actually degenerates even more if you go down in this diagram. So now this is the Petrov type according to this classification. And the type, if the roots become to coincide, they degenerate. So the 1 goes to the 2 if the roots coincide. The 1 goes to the 3. This 1 root becomes that one. So you have this arrow here. And the null case is the 4 roots here. So you get that arrow. And then you can also go for 1 to D if you have these double roots that coincide, etc. So this is the entire summary of the degeneracies of the roots. So the Petrov type D is the one where you have 2 and 2 degenerate roots. So you have 2 distinct principal null directions that are degenerate. So a Newman Penrose tetrad is adapted to this null direction, where you have psi 0 and psi 1 that vanish in general. Well, you have psi 2 that vanishes, so that's a Kinserly tetrad. But if you can find also a frame where psi 3 and psi 4 vanish, it's a special tetrad, and that's called Kinserly tetrad. So for the Kerr metric, this is the case. So for the Kerr metric, it's Petrov type D, and you can find this Kinserly tetrad where only psi 2 is non-vanishing. And the interesting things, the additional theorems that say, for example, this Goldman-Sachs theorem that say that if you have a type D spacetime, the principal null congruences, null directions are shear-free geodesic congruences. So there are congruences of geodesics that are in addition shear-free. So that shows that this Newman-Penrose formalism is actually very suited for describing the gravitational wave in Kerr because of all these properties. So Kerr is type D, only one psi is on 0, and then all this, you can have a frame adapted to this principal null direction, which are shear-free geodesic congruences. And so that describe naturally directions for gravitational wave propagation. Okay, so with all this background, we can arrive to the quasi-normal modes. So we look at linear perturbations of matter or of the metric on the Kerr geometry. So all these linear perturbations are denoted as some field. So it either is the metric or is the matter with some index which delivers all the possibilities. So if you have such perturbation, it depends a priori on 4 spacetime variables. But there are 2 Killing vectors of Kerr. If there are 2 Killing vectors of Kerr and you choose T and phi to be the one where that are such that the metric is independent of T and phi, there's no explicit time and angular independence in the field equations. So the linear solution, you can decompose it in isolated Fourier modes. So isolated in T and phi, where since phi is periodic, M is discrete, and T is continuous, so omega is continuous. So the resulting linear equations will be partial differential equations in the remaining R and theta. This partial differential equation will depend upon the mass of the black hole and angular momentum. So J over M is called A, standard notation. And this equation will depend, of course, on M and omega. So these are very complicated equations. So the boundary conditions that you impose to these equations to finalize the system is 2 sets of boundary conditions. You want them to be ingoing at the horizon. So you want each set of modes around the horizon to be ingoing, in the sense that you have so you have to define good coordinate system close to the horizon. So I don't know if you had that in your GR class, but if you want to parameterize Kerr close going to the horizon, you can define Eddington-Fickenstein coordinates, which pass through the horizon. And for that, you define a tortoise radial coordinates and a tortoise angular coordinates. So you can define this ingoing condition very precisely by requiring that you are ingoing in the sense that you have a minus I V star here. So you just need to know that this is the condition that you need to impose. And then for the outgoing condition at infinity, it's called also the up condition. You need to look at the asymptotic behavior close to non-infinity. So so you go to retarded time. So t minus r is the asymptotic flat retarded time, and you want it to be outgoing. So to have a minus I here, so that you are outgoing with respect to non-infinity. So you impose these two conditions. So note that these conditions are imposed in different places, at the horizon and at infinity. So I can do a Penrose diagram of this. So here is the Penrose diagram of Kerr. So in this Penrose diagram, all null rays are preserved with this conformal transformation that I used to draw this diagram. So the null rays go at angles of 45 degrees, and the infinity is brought to finite distance. So the horizon are here. There are these null lines here, and the future time-like infinity is here. The past time-like infinity is here. Special infinity is here. Your future time infinity is here. Past time infinity is here. This is the ergo sphere, but we don't need to know that. So the boundary condition here is that you are ingoing at the horizon, at the future horizon, and you are outgoing at non-infinity. So if I draw a fixed time in this, so if I take a space-like slice here, so it means that we have a linear partial differential equation with boundary condition at two different places, at the horizon and the infinity. So these are called the boundary value problems. So when you have a boundary value problem and you solve a linear PDE in a boundary value problem, you have an infinite set of solutions. So in this case, this infinite set of solutions will be labeled by some harmonic numbers. So the M, we already defined it, but there will be an additional one. It's a generalization of spherical harmonics, and some so-called overtone, because there are different solutions, different types of modes here, which can have well, you have an additional parameter that will be necessary. So so the frequencies, if you solve this linear problem, the frequencies will have a real part and an imaginary part in general. And so if you have an imaginary part, if you look at this, an imaginary part if you have a positive imaginary part, it will give you something which is increasing in time. So that would be a linear instability, because you will have a mode that will grow, whose amplitude will grow in time. Instead, linear stability is equivalent to that all these imaginary parts are negative. And actually, that's the case. For Kerr, you have linear stability, so any perturbation will decay over time. So to solve this system, you need to master, to solve this linear PDEs, and you need to impose the boundary conditions. So far, it's still a very complicated problem because you have coupled linear PDEs. So the breakthrough was done in 72. So Tukowski was a PhD student of Kip Thorne, and he was assigned by his advisor to solve that problem. And he found a way to separate the radial and polar equations. And for that, he used the formalism, the Newman-Penrose formalism. So he wrote down the linear perturbation equations in terms of this Weil-Newman-Penrose scalar, and he used for that a Kinserly tetrad, a tetrad which is adapted to the null direction of Kerr, which are given by this spectrum of type D. And so because of this analysis, it's possible to find these principal node directions and to find the tetrad adapted to Kerr. So you had to use these two tools. So in Boyer-Lindquist coordinates, the standard coordinates of Kerr, there is only the psi2, which is non-zero, which contains both the mass A and contains it's a function of r and theta. So that's the value of psi2. So what you want to study is the linear perturbations. So you want to study the linear perturbation of this size. So you have 5 different perturbations of each of the complex Van-Neumann-Penrose scalar. And what you have to what he was able to show is that if once you know these variations of either delta psi2 or delta psi4, you can reconstruct the others up to just a change of MNA, which are included in this variation of delta psi2. So you need to understand either the variation of delta psi0 or the variation of delta psi4. So the proof takes a bit of time, but you can see that there is differential equations that allow to relate the others. And now his insight is that these two things, these two variables, so delta psi4 times this one, or delta psi0, they are separable. That's separable equations. So if you call psi either of the two, and you assign you say that this is s equals plus 2, this is s equals minus 2, you can write this equation in terms of the new s variable that just introduced, which is plus 2 or minus 2. So this is the equation that Tukowski found. And in that equation, what really works is that you see that there is a dependence in the radius, which is here. So delta is this delta is vanishes on the horizon, and so this is this r squared minus 2mr plus a squared. So it's a function of r only here. All this is a function of r. You have a function of r here. Here your independent term of r and theta. Here is a function of theta. Here is r, and here is theta, and here is r, and here is theta, and here is theta only. So it means that you can separate the equation with some separation constant. So from there, you define, so this side, you define a separate function of r and a function of theta, or cos theta. It's actually better to use cos theta as a variable. And you need to write this down, you need a separation constant. So that separation constant is called epsilon E here. It will depend on additional label that will label the different constant that will appear. So this is how this L appears. So here is the equation, the equation you find for this variable. So cos theta equals x, and this is the equation, so second order equation. And for the radial part, this is the equation you find. So there is some potential, and there is some source. In this one, there's no source. It's just an homogeneous equation. So let's look at these two equations. What you get? So when a is 0 for Schwarzschild, there is no dependence in the frequency anymore, because you see they will always have a omega appearing here. So the frequency, that frequency drops out, and then these one. If you in addition you put s, this s that I wrote down here, if you put s equals to 0, you find that actually this is exactly the spherical harmonics. So for s equal 2 or minus 2, it's a generalization of spherical harmonics. So the L and M are natural numbers appearing for the spherical harmonics. But when you have this spin, so this s so equal to of minus 2, these are called generalized spherical harmonics, and these angular space separation constant are not known analytically, so you need numerical methods to solve them. So the radial equation is given by this one, and again when a equals 0, the m dependence drops out. So, and all this A dependence that drops out actually is a consequence of SO3 symmetry, because when you do a rotation, you should not have any difference. Okay, so once you are
Sorry.
there, well, you need to, well, maybe I should stop for questions here.
Sorry, Geoffrey, this angular equation is, I guess, somehow known. I mean, we know the set of solutions, right?
Yeah,
been
so
weighted,
yeah.
But the
So it's
radial
not-
equation, is it some known mathematical equation, or?
yeah, so it's a particular confluent Earn equation.
Sorry, could you repeat?
It's a particular confluent Earn equation.
Okay.
Yeah, and the first one is as well is a particular confluent Earn equation. So in the mathematics literature, there are special cases of these special type of functions. So yeah, so yeah, that's you can define a special function which is obeys that equation. So that's the best you can do with a special function. So it's not it's not a hypergeometric function. It's more general than that.
Right, but I can write down a basis for solutions to the angular equation, but can I do the same for the radial?
Yes. So yeah, so you have two independent solutions. And you can numerically obtain them from solving this equation. And there is a name for them in the mathematics literature. You can write them in terms of confluent Earn equations.
Okay.
So actually, this is so in the literature, these equations have appeared and they've been derived and rederived by many authors. So there are several ways to solve them. And everybody in the literature is doing a different methods to solve them, it seems. So the original way it was solved, it was done by Lever, and he used a continued fraction method in '85. So I'm not going to explain that in detail, but if you can have an ansatz for how these functions behave close to the two poles of the equation. So at the poles when theta is 0 and pi, x is +1 and -1, and you can see that there are poles in this equation when x is 1 and -1. There's another pole when x is infinity. So there are three poles: infinity, 1, and -1. So you can make an expansion of this of that one around the poles, and then have some Taylor type expansion around them. And you can use some matching between these expansions, and you arrive to continued fractions for solving them. Then you can numerically implement the continued fraction, and that gives you a way to evaluate them. But since you have a boundary value problem, you can use any methods to solve boundary value problems to solve this method. So very familiar one is spectral methods. So you can write down some tests, some complete basis of function in the interval. So here I'm talking the real problem, yeah, but this is also a boundary value problem for theta. So here it's a boundary value problem because you have boundary condition at the poles. So at theta equals 0 and theta equals pi, which are the two north pole and south pole, you want the function to be regular. So you have a boundary value problem in the sense that it's regular at the two poles. And you want to solve in the interval between the two poles. So it's a boundary value problem, and you can use spectral methods, for example, to solve it. So any numerical methods that you want to solve this kind of problems can be used. So the literature, there was a Lever method, but you can use spectral methods as well. So there are several implementations of this in this of this equation. So in the black hole perturbation toolkit, I strongly recommend to look at this if you are interested to find the solution of this problem and to work out the numerics. You can there is a lot of material that has been done because you don't want to reinvent the wheel each time, and there are several methods that are there. And there's also Mathematica in the latest version, 12.1, now implements the Earned type function. So that solves the spin-weighted toroidal harmonic equation. So but that's only in the latest version of Mathematica. So for the radial equation, there are several methods that I use as well to solve it. And I'm not going to discuss that, but you can numerically implement it. Okay, so once you have set up that problem, so for this is clear now how the L appears. So for the radial Tokowski equation now, so once you solve for A equals to 0, you see that these two equations totally decouple. For in terms of the frequency appears only here. Because there is a frequency times r squared, the frequency disappears here. But once A is non-zero, you have to solve at the same time the two equations because the frequency appears in both. So there is a coupled system. There's just two equations. So so you can numerically solve it, and here are the results. So you can see this review of Berti, Cardozo, Starinets, which is a great review. And on the home page of Emmanuel Berti, you can download the data of the quasi-normal modes that you can replot yourself. So this is what I did here. I took the data and replotted it. So we're looking at S equals 2, and so you can increase the L value, and you will have different modes. There's no dependence in M because M drops out totally for Schwarzschild by spherical symmetry. So each point is a quasi-normal mode, and you see that there are many different quasi-normal modes, and you can label them using the N, the overtone. So N is an overtone, and for each value of N increasing, you have higher and higher overtones, which means lower and lower imaginary part of the frequency. So all the frequencies, the imaginary part of the frequency are negative, so you depict usually minus the imaginary part in this axis. Otherwise, the graph will be in here down. So the fact that all of them are negative, it means that you have linear stability. Here's the real part. You see that the graph is symmetric with respect to the real axis. You can see that in the equations, that symmetry in the equations. I don't recall how you see this, but yeah, when A is 0, you have an omega squared here only. Here you have an omega. So it's not immediately clear why the real part will be symmetric here. Yeah, I don't remember how to see it directly.
Sorry, when A is 0, it's the Schwarzschild, right? So
it's a Schwarzschild, yes.
I mean, like, it shouldn't matter the orientation. I mean, the M. This is
the M, yeah, the M dropped out here. So this is just
about omega. Oh, yes,
the real part of omega. So it's just that it's symmetrical with respect to the real part of omega. So, but the real part of omega is, I think, is because the real part of omega you can just exchange time, right? So omega. So if you flip t to minus t, the metric will not change, and you will change the sign of omega. So it's just that. So there's this symmetry that you can exchange omega and t at the same time. And if you change time, the metric doesn't change. So this is why it's symmetric. And now for increasing values of L's, so this is L equal 2 here, and this L equal 3 is here. And you have note that there is a very special algebraic values where the frequency is identically 0. So for each L, there is 1 actually. 1 is here for L equal 2, 1 here for L equal 3. Astrophysically speaking, the most important one is the most weakly damped. So the lowest one, which is not very clear here, but it's here. So its numerical value is given by here. So this is the most weakly damped mode. So most weakly damped means that for very high imaginary part, it means that it decays very fast. Decays very fast because if I go again here, so if you have a large imaginary part, a negative imaginary part, it means that you are exponentially very quickly decaying. So astrophysically, what you want to measure in this quasi-normal mode signal is the most weakly damped modes. So the interesting one is this one. And so these values are just scale inversely proportional to the mass. So if you're able to detect this quasi-normal mode ringing inside of a black hole merger, you have a direct probe of these two numbers, and you can check the ratio. You have to check that the ratio is compatible with this. So actually, I didn't tell you, but if you put the values of S, you can actually, the Tukowski equation actually is the one that describes scalar, vector, and gravitational perturbations. So far, I only talked about S equal to 2 gravitational ones, but the equation is actually the right one for describing scalar and vectors. For the scalar case, psi is actually the scalar itself. For the vector case, you have to work out exactly what you mean by psi. So it's some function of the stress energy of the f mu nu. It's so some projection of the f mu nu with the Newman-Penrose tetrads. Okay, and then for values of S, you have different type of quasi-normal modes. For Kerr, then there are two features that are important. So again, the most weakly damped mode now has a spin dependence, and you can make a numerical fit of it. And the interesting one is this value, which is a good numerical fit. And so now you see that there is explicit spin dependence in the ratio between these two numbers. So if you have just one quasi-normal mode, you can deduce two values. So you can use A and M of the final black hole. So if you want to do a Kerr test, a test of the Kerr metric, you will need to do to have at least two quasi-normal modes. Because if you have two quasi-normal modes, then the second one will also have a fixed dependence in M and A, and you have two tests of the Kerr metric. So this is the numerical, or the observational challenge. Now, because now there is a spin, there is a dependence in this mode M, and that's called the Zeeman splitting by analogy with the lines in the hydrogen atom, where you start to have additional forces that make you a dependence in the angular momentum. But it's the same here for Kerr. There's the same type of splitting because of M. So there is a very nice video explaining all these quasi-normal modes. So I will now skip. I will now go to this video here. All right. So can you see the video?
Yes.
Yes. Okay, so this comes from a paper where the authors did a very high accuracy study of the quasi-normal modes of Kerr, and they represent the numerically what they are from L equal 2 to 12 with the first 8 overtones. They put some interesting music. It's good to finish the class. So here is the case. I don't know if you can see. So yeah, at the very top, you see this is A equals 0. In the previous plot, I showed you only L equal 2. And here, since there is this symmetry with respect to the real axis, we only depict the right part, the real part being positive. So this is, and again, it's minus the imaginary part of the frequency. depicted on the vertical axis. So when you increase L, you have additional lines appearing here on the right. And each line depicts different overtones. So you have the lowest overtone below and higher overtone in higher. So now when you turn on the angular momentum A, you will see the Zeeman splitting that will start. So just explaining the overtones, L equal 2, equal 3, equal 4, etc. And now here's the spin that arises. So at this point, for very low spin, you will just see that there is well, you see that this quasi-normal is changing, but actually it's changing depending, it's moving in different places depending on the value of M. So for L, so the different values of M, well, it depends on it depends on L, of course. So for L equal 2, you have M equals 2, M equals 1, M equals 0, M equals -1, M equals -2. So you have 5 lines. For L equals 3, you have 7 lines. And then you have more and more lines here. So it becomes quickly very messy. But you see each of them, each of values M corresponds to a separate well, quasi-normal modes. And you see these quasi-normal modes are the endpoints of these lines. And now the interesting thing is that if you increase the spin high enough, there is some phenomena that occurs. This is the value for 1. So here something weird happened. You see that some quasi-normal modes remain with the non-trivial imaginary parts, but some of them just go towards 0 imaginary parts. So, so close to extremality, some quasi-normal modes actually are becoming non-damped, undamped. So they are very, very slowly damped. And this feature is because of the near horizon geometry appearing in the extreme case. So this is a feature. I don't know if you talked about that in the class, GR class, but when you have a near extremal black hole, there is a new space-time region that opens up close to the horizon of the black hole. It's called the near horizon geometry. So the quasi-normal modes that somehow are emitted in this near horizon geometry have a time redshift because there is a redshift of that near horizon region with respect to the asymptotic region. And because of that redshift, as seen from the outside, all these quasi-normal modes are highly damped. And this is the feature that you can see visually here. So that's the end of this video. Right. Yes, you have questions about this quasi-normal modes?
Yeah, is this some particular can you go at the end of the video, please?
Yes.
There seems to be like integers or half integers, the modes that go to 0 imaginary part. Is this relevant for something, or is?
Yes, it's true. It's true. Yeah, so this in the so basically it's because the frequency, the angular velocity of extreme Kerr goes towards 1/2m.
Yeah. Okay.
So all these quasi-normal modes that arise in the near horizon geometry, they have a real type of the frequency which is actually fine-tuned to be so these ones are co-rotating because they belong to near horizon geometry. The omega has to be 1/2m, which is the angular velocity of the co-rotation angular velocity of the near horizon geometry, plus small perturbations. And this is why you have this half integer coming up here. So there have to be multiple of this fundamental angular velocity of extreme Kerr, so which is 1/2m. So this becomes proportional to 1/2.
Okay, thanks.
Sorry, close to extremality, can we solve the equations analytically?
Yes, so there is an analytic formula indeed at lowest order. So if you do these continuous fraction methods, you find actually to find these quasi-normal modes is a solution of some equality involving gamma functions, and you can then make an approximation in the extreme zone, and then you find analytic formula leading order that you can perturb around. But it's very difficult to do because you need to work out with well, you need to know your complex analysis well to do this,
right.
this analysis, to do that. All right, so so that's concludes the class about the Kerr. So that was the Kerr spectroscopy. So I don't have time to explain about the amplitudes and how to compute them, but for that you need really numerics, because you need to solve your two-body problem to be able to find the amplitude at which all these quasi-normal frequencies are triggered at the end of the merger. That depends upon the source. So that's an entire problem to solve, which is harder. Do you have more questions about this lecture, or any question actually? Okay, so well, I hope you were able to get some hints into those topics. I will give you all the lecture notes that you can review, and you can do the exercises more slowly. I didn't have enough time to really do the exercises thoroughly, but if you have more questions, feel free to ask me later by email, or you ask me for a chat.
I have a question. I don't know if it makes a lot of sense, but I mean, kind of phenomenologically. So if you have a merger of two black holes in holography, what kind of phenomena would that represent on the QFT side?
Well,
phenomenologically, without any like specific dual in mind.
Well, first you need to tell me what kind of holography you're thinking about, because if you have just two black holes in assembly flat space, there's no obvious holographic dual.
No, in ADS-CFT, for example. Yeah.
In ADS-CFT, okay. So now if you imagine that you have a black hole merger in ADS, right? So when you final stage of the merger is when you have a single black hole, is corresponds the dual CFT to a thermal state. So you will approach the thermal state. So what you are doing is you are thermalizing your system, because it's the end state of collapse is the thermal state. So you start with a state which is out of equilibrium, and you will reach towards the thermal state. But now it's a very specific state outside of equilibrium, because you have two separate density of energy at different places. So the dual of that would be well, a stress energy tensor that contains two spatially separated parts, which tend to mix up. So so maybe the best analogy is to have two baths, two thermal baths. If you have two black holes that you put together, and then they thermalize. So that's the best way to do a black hole merger. To think about the black hole merger, you have you have two heat baths, which are two black holes, because both of them have a specific Hawking temperature that when they are well separated, and then you put them at finite distance, and so these two heat baths will just exchange. Well, there's more than just a thermal exchange, because that would be just due to the radiation. There is really a physical way that they come close to each other. There is a Newtonian force between them, but the Newtonian force in ADS-CFT is not very clear what it is. So just the gravitational attraction, the 1/square law force. You have to understand what's the analog of that in the CFT. That's not totally clear to me what it is.
And so in the gravitational waves, the energy radiated by gravitational waves that goes up to the ADS boundary, how will that just be like small perturbations to the boundary stress energy tensor, or?
So in ADS-CFT, you impose always reflective boundary condition at the boundary. So the waves bounce off in the interior. So if you want to have like waves that physically get extracted from your ADS, which is closer to the asymptotic flat case, you have to impose like leaky boundary condition in DS, which corresponds in the CFT language to have an open system, to have a CFT coupled to an external bath. And then you allow energy to leak out of your system. So the stress energy tensor is the model of all the energy that is inside of your system. So all the gravitational waves inside the system and your massive two bodies. And now if you couple your CFT to an external bath, you will allow the gravitational wave to leak out of your spacetime once they reach the boundary. So that's how you could model that.
And while if we do this in a sort of flat space holography, where the gravitational waves that we send to the boundary will have a memory effect, like we were discussing in the advanced GR lectures. And so that will change the state of the CFT, ideally. I mean, I know it's not something concrete, but...
well, yeah, so, well, the memory effect is only one part of the effects, and each time you have a Weit tensor reaching the boundary, you have it's hard to disentangle that effect from all the others. There is really no flat space holography at this point that is capable of making a clear statement about these black hole binaries. But maybe it's possible to understand first in ADS-CFT how you would describe a black hole merger, and find if there is an analog of this. If you want to understand memory effects, memory is really related to the BMS group, and you first have to understand how you generalize that in ADS. So I've recent work on that in that direction, but still there's no clear relationship. Well, there's no clear definition of memory in ADS or in the CITR. Actually, it's a topical research now.
Okay, thank you.
Okay, some other general questions, feel free to ask.
Sorry, these generalized killing vectors, is it only implemented in this context, or is it more widely known or used in other?
So they are not really well known. So they originate from the work of Dixon and then Art that re-understood it in a more general way, introduced and got into that concept. So I think that there could be a more general use of it. So this is why I was really interested to read about it and to present it this way, because I find it very intuitive first to derive these equations of motion this way, and I find also that so all this technology has been worked out and has not been widely used. So it could be interesting to think about it more deeply.
Right. Is there a reference in the lectures that we can?
Yes. So it's I think I put the reference art. Yeah. 2008. I think he has only 1 or 2 papers or
I'll find
papers that year, so you can find it easily.
Yes. Thank you.
Any other question? Okay, so well, I hope you enjoyed it, and don't hesitate to ask me later questions by email. Okay, bye bye.
Bye bye. Thank you.
Thank you. Bye.
Thank you.
Thank you. Bye.
Thank you. Bye bye.